All right, good day, everyone. How are you all doing? In today's class, our emphasis will be on continuity of a function. In our previous class, we have been able to define what a function is, and we also talked about the types of functions. We would mention the one-to-one, the onto. I'm not going into all of those types, functions and all that. We have already dealt with them. If today is your first time in this class, please go through all the lectures. Then we talked about how to find the domain of a function. Then after that, we proceeded to limits of a function, which is how a function behaves as x approaches a certain value. Then we talked about the methods that are used in finding limit of a function. We mentioned direct substitution. We mentioned by factorization, by rationalization. We mentioned by limit at infinity. We mentioned by the use of L'Hopital's rule, the series expansion method. But in today's class, we want to see what does it mean for a function to be continuous. And for a function to be continuous, there are three steps you must have to take note of. There are three cardinal conditions for a function to be continuous. The first condition is that I said for a function f of x to be continuous at x equals to what? A. We have three steps. Number one is that f of a must be defined. F of a must be defined. F of a must not be undefined. It must be defined. Okay. Number two is that limits of f of x as x approaches a must exist. And this simply means that limit of f of x as x approaches a on the left hand side must be equals to limits of f of x as x approaches a on the right hand side. This is what it means for a limit to exist. Number three is that these two must be equal, meaning f of a must be equals to limits of f of x as x approaches a. So if these two are the same, that means these are the three conditions. It means that the function is continuous at that particular point. For a function to be continuous at x equals to a, f of a must be defined. If f of a is not defined, it means the limit is not continuous. If the first condition fails, that means the limit is not continuous. For example, if I have f of x to be equals to 2x divided by, let's say, x minus 3, and we are asked to find the continuity of f of x at x equals to 3. By the time we put the value of x as 3, that will give us 2 times 3 divided by 3 minus 3, and that will give us 6 over 0. It gives us an undefined function. Right? When divide 6 by 0, we have an undefined function. So that means that the limit, my f of x, cannot be defined. It's undefined. It means that this function is not continuous at x equals to 3. Okay, but if f of a is defined and the limit of f of x does not exist, it simply means the function is still not continuous at x equals to a. What does it take for a limit to exist is that the limit of f of x as x approaches a on the left hand side must be equal to limit of f of x as x approaches a on the right hand side. All of this I'll be explaining. I will be solving so many examples from textbooks and from past questions. Now, if your limit exists, if these two sides are equal, it means your limit exists. The third condition must also exist in the sense that f of a must be equals to limit of f of x. Let's say, for example, if f of a is gotten as 3 and your limit is gotten as 3, it means f of a and limit are both equal. That means that the function is continuous at that particular point. But if f of a is 3 and limit is 4, limit f of a can be defined. Limits can also exist. But if these two are not equal, that means the function is not still continuous. So the first thing we need to take note is that f of a must be defined. Number two, limit must exist. Number 3, f of a must be equals to what? Limit of f of x as x approaches what? A. Now let's see some examples from the textbook and from past question. Now let's see some examples from the textbook and from past question. But don't forget these 3 tests. We have 3 continuity tests for continuity of a function. The first test is that f of a is defined, limit must exist, f of a must be equals to limit of f of x as x approaches a at that point. All right, but a major point that defines that a function is continuous at a particular point is the third condition. Is this third condition that says that f of a must be equals to limit of f of x. In our previous class, we have learned a topic called limit of a function. Please, I will advise every one of you in this class, if you know you have not gone through that class on limit of a function, because after limits of a function, we then talk about continuity. If you don't understand limit of a function, there's no way you can understand continuity of a function. In fact, we have to start with understanding the word function, limit of a function, all right? Then continuity of a function. And all of this class we have done in our previous classes. So take note that there are 3 conditions for a function to be continuous at a particular point. The first condition is that f of a is defined. I've already explained what it means for f of a to be defined. Number 2 is the limit of f of x as s approaches a must exist. What does that mean is that for this to exist, it means the limit of f of x as s approaches a on the left hand side must be equal to limit of f of x as s approaches a on the right hand side. If these two are not equal, that simply means that the limit does not exist and the function is not continuous at that particular point. But for this to exist, simply means these 2 conditions, this must be equals to each other. Then the final condition, which is the general condition, is simply that f of a must be equals to a limit of f of x. If you look at this very well, these conditions, the third one covers for both the first and the second. One is that f of a must be defined, limit of f of x must exist, then f of a must be equal to limit of f of x. Now let's see some examples. Let's see some examples on how to find the continuity of a function at a particular point. All right. Example 1. Okay, we have a question that says that determine if f of x equals to x plus 5 divided by x minus 3 is continuous at s equals to 4. Here we are given a rational function, right? A rational function. We have to determine if f of x is equals to this is continuous at s equals to 4. So what do we do for solution? The first step says that f of a must be defined, right? Okay, in this case, our a is s equals to 4. Let me repeat the conditions. The first condition says that f of x, for f of x to be continuous at s equals to a, the first condition says that f of a must be defined, right? Must be defined. Number 2 is that the limit of f of x as s approaches a must exist. Must exist. Okay, and this simply means that limit of f of x as s approaches a on the left hand side must be equals to limit of f of x as s approaches a on the right hand side, right? Then the third condition says that f of a must be equals to limit of f of x as s approaches a. Okay, so the first is to define f of a. In this case, we are asked to determine if f of x is continuous at s equals to 4. So the first is to determine f of 4. In this case, our a is 4, right? So for f of x to be continuous at s equals to a, s equals to 4, so it means I will substitute my x as 4 to define f of 4. So let's define f of 4, which is the first condition. F of 4 will give us 4 plus 5 divided by 4 minus 3. What does that mean? Is that to define f of 4, it means anywhere we see x, we just substitute the value of x as 4 in f of x. And that will give us 4 plus 5 divided by 4 minus 3. This will give us 9 over 1, which is equals to 9. So we have been able to define f of 4 as 9. The second is to define the limit of f of x. The limit of x minus s plus 5 divided by x minus 3 as x approaches 4. As s approaches 4. If you look at this, if you go through my class under limit of a function, we have different methods used in finding limit of a function. The first method is called direct word substitution, right? We say that if we use direct substitution to find the limit and we have an indeterminate form or we have an undefined form, the next is to try either by factorization or by other methods. And we listed the methods. We have the L'Hopital's rule, we have the rationalization method, we have a series expansion method. We have so many methods we listed, right? So the first we have to do is to try direct substitution, and that will give us the same thing, yeah? It simply means to find my limit as s approaches 4, I'll substitute my s as 4. It means 4 plus 5 divided by 4 minus 3, which is same as 9 over 1 equals to 9. What do you notice here? F of x, f of 4 is 9, limit is also 9. So the third condition is that since f of 4 is equals to the limit of f of x as s approaches 4, right? Our f of x is this, right? Since the limit of f of x as s approaches 4 equals to f of 4, and this is equals to 9, therefore, the function f of x equals to x plus 5 divided by s minus 3 is continuous at x equals to 4. It simply means it is continuous at s equals to 4 because our f of 4 gave us 9. Our limit of f of x gave us 9. Since f of 4 and f of 2, this first and the second are the same, that means the limit, that means the f of x is continuous rather at s equals to 4. All right, guys, let's see number 2. Question number 2 says determine if f of x equals to s squared minus 9 divided by s minus 3 is continuous at s equals to 3. We already know the 3 tests for continuity of a function, which is f of a is defined, limit must exist, and limit of f of x must be equals to f of a. Okay, so let's see the first condition. Let's see if f of 3. We have to test if f of 3 is defined, meaning I will have to direct substitute the value of x as 3 into my function f of x, and that will give us 3 squared minus 9 divided by 3 minus 3. This will give us 9 minus 9 divided by, let's say, 3 minus 3, and that will give us 0 divided by 0. This is not defined. This is an undefined function. This is an undefined function. That means that condition 1 failed, right? The condition 1 says that f of a must be defined. But in this case, we have an indeterminate form, which is an undefined form. That means condition 1 failed. Since condition 1 failed, it means that f of x is not continuous at s equals to 3. We have only failed condition 1. That means f of x is not continuous. So, but let's see. Let's see condition 2 that says limits of f of x as s approaches 3 must exist. Meaning that, in our previous class, we learned how to find limit of a function. We say once we apply direct substitution and we have an indeterminate form, the next thing we need to do is to either factorize, or we rationalize, or we apply any other method. But for this, the simplest method that can be used here is actually by factorization. Okay, so let's look at this. We have to factorize this expression. By factorization, we can factorize it using the principle of completing the square. No, we can use the principle of difference of 2 squared, right, to factorize, and that will give us our x squared minus 3 squared divided by x minus 3. Is that clear? Okay, from the principle of difference of 2 squared, this becomes x plus 3 times x minus 3, all divided by x minus 3. All right, so these two can divide, and that will give us x plus 3. So by the time we substitute the value of x as 3, this will give us 3 plus 3 equals to 6. So that means our limit of f of x as x approaches 3 is equals to 6. This actually exists, right? Limit exists, but f of 3 is undefined. So since f of 3 is not equals to the limit of f of x, therefore the function f of x equals to x squared minus 9 divided by x minus 3 is not continuous at s equals to 3. We call these types of discontinuity whole discontinuity. Whole, also called the removable discontinuity. When we experience a whole discontinuity function is when f of a is not equals to the limits of f of x as s approaches a. When f of a, like we saw, is not equal to the limit of f of x, we say the function is not continuous. It's called discontinuous function. And that kind of discontinuous function is called a whole or a removable discontinuous function. Let's see another example. Okay, we have a question that says that we should test the continuity of the function at s equals to 4. We should test the continuity of the function at s equals to 4. We already know the test for continuity. We have the 3 cardinal tests. We have the first test that says that f of a must be defined for f of x to be continuous at s equals to a. The first is that f of a must be defined. Number 2 is that the limit of f of x must exist. Number 3 is that both f of a being defined must be equals to the limit of f of x. Okay, looking at we are given 2 functions. We have the first function and the second function. For the first function, we are told that f of x is equals to 4 minus x divided by square root of x minus 2 when x is not equals to 4, right? That means that the domain of x are all values apart from 4, right? The reason because by the time we put the value of x here as 4, that will give us root 4 minus 2, which is 2 minus 2. At the end of the day, we're going to have 0 over 0, which gives us an indeterminate form or undefined form. So definitely s must not be equals to 4. Then here we are told that the second function is 1 over 4. We are told that this function is at s equals to 4. So we are asked to find test for the continuity of the function. So the first is to define f of 4. We are testing at s equals to 4. We have to define it. Number 1, f of 4. We are told that the f of 4 is given as 1 over 4. This is defined, right? We have defined this. Number 2 is to test for the limits of f of x. The limit of f of x, this limit f4 minus x divided by root x minus 2 as s approaches 4. We have to find the limit of f of x, the limit of this we have defined that f of 4 is equals to 1 over 4. Now, the second is to find the limit of f of x. I've already taught us limits. We say that in limit, we have different methods, right? Using finding limit of a function, we have the first method, which is called by direct substitution. Number 2, we have by factorization method. Number 3, we have by rationalization method. Rationalization method. This is also called the conjugate method. We have other methods down to limit at infinity. We have the L'Hopital's rule. We have the series expansion method, also called the Taylor's method. Now, we say that if direct substitution gives an indeterminate form, meaning 0 over 0, okay, we have to apply other method. Definitely, this will give us 0 over 0 by direct substitution. If I'm to put the value of x as 4, I'm going to have here as 4 minus 4 divided by roots 4 minus 2, which is 0 over 2 minus 2, which is 0 over 0. Are we there? And that will give us an indeterminate form, meaning I cannot use direct substitution. All right. Number 2 is that I can't use by factorization because I cannot factorize this. And I said in my previous class on limits that whenever you have a square root function, that implies that the only method that can be used is simply by rationalization method. We have to rationalize the denominator of this function by multiplying the conjugate of the denominator by the numerator and the denominator itself. Now let's see how that goes. So since this gives us 0 divided by 0, which is an indeterminate form, we have to rationalize the function, the given function. Okay, and now give us lim 4 minus x divided by with x minus 2 as x approaches 4 to be given us 4 minus x over with x minus 2 times with x plus 2 divided by with x plus 2. Don't forget that we say that by rationalization, we mean we multiply the conjugate of the denominator given by the numerator and what? Denominator. The conjugate of with x minus 2 is with x plus 2, right? So I'll multiply the conjugates of this with the numerator and denominator, which is what I just did here, right? So what we do next is to simplify what we have there. So let's simplify this and see what we're going to generate. At the end of the day, let's multiply 4 minus x with this. This will give us limit. Let me call this f of x. That will give us 4 minus x times with x plus 2 divided by. Let's multiply the conjugate of this with this. With s times with x will give us x. With x times with s will give us with square root of s squared. Square can go with this, and we're left with x, right? So that's why we said we have x here. So we have here to be x. So with x times 2 will give us plus 2 with x. Minus 2 times with x is minus 2 with x. So minus 2 times 2 will give us minus 4. Okay, 2 with x minus 2 with x is 0. This will cancel out. So we are left with, this is as s approaches 4, right? So we have our limit of f of x as s approaches 4 will be 4 minus x times root x plus 2 all divided by, we are left with x minus 4. Now, if you look at this, these two expressions look similar, but not really exactly the same. Here we have 4 minus x. Here we have x minus 4. Now, we're going to think out a way where we can make them to be the same so they can easily cancel out. All right? So, let's see what we're going to generate at the end of the day. This will give us limits of f of x as x approaches 4 to be equals to 4 minus x times with x plus 2. Don't forget that we say that if we are to multiply by the conjugate of the denominator, I will not evaluate the numerator. I will just leave it this way. The only part we have to evaluate is what? The denominator. If I have to multiply by the conjugate of the numerator, I will not evaluate the denominator. I will just only evaluate what? The numerator. Because sometimes this square root can also be on the numerator. We can have the whole of this here. We can have the whole of this here. Are we there? Meaning this can come up, this can come down. So if this is up, it means I'm going to rationalize the word numerator by multiplying the conjugate of the numerator by what? The denominator and the numerator itself. Okay, so please take notes. So here we have divided by, let's rewrite this. This can also be written as minus 4 plus x. Am I communicating here? Minus 4 plus x. So let's finalize the expression. We can also rewrite this as limit of f of x as x approaches 4 to be equals to 4 minus x with x plus 2 all divided by. How do we make this to be equals to this? How do we generate the same expression here? Let's say minus is the like terms. In brackets, can I say this is same as 4 minus x? We have seen that this is same as this, right? Okay, these two, they are the same. Plus x minus 4 is same as minus 4 plus x. Then by the time we bring a minus sign here, it's still the same as this. Let's check this out. Minus times 4 will give us minus 4, right? Minus times minus x will give us plus x. So these two, they are the same. All right? When you evaluate this out, you will fall back to this. Now we have been able to generate common term. So this can go with this, right? So if that should occur, let me take off this. If that should occur, that implies that our limit of f of x as x approaches 4 will then be, divide this by minus 1, that will give us minus in brackets with x plus 2. This will then give us minus root 4 plus 2. And that will give us minus 4. Minus 4. Because root 4 is 2. 2 plus 2 is 4. 4 minus will give us minus 4. That means our limit of f of x as x approaches 4 is minus 4. What do we notice here? Our limit is not same as f of 4. We said for a function to be continuous at a particular point, we said the function must satisfy 3 conditions. The first condition is that f of a must be defined. If a is 4, meaning f of 4 must be defined, which we have seen, right? Number 2, the limit of f of x must exist. The limit exists, and the value is what? Minus 4. Number 3 is that f of 4 must be equal to the limit of what? F of x. But if you look at these two, they are not equal. So since f of 4, which is equals to 1 over 4, is not equals to, right, limit of f of x, which is equals to minus 4. Therefore, the function f of x is not continuous at x equals to 4. We call this type of discontinuity a whole discontinuity, also called removable, a whole discontinuity. When f of a is not equal to the limit of f of x as s approaches a, it's called a whole discontinuity. All right, so let's see another example. All right, this question says we should test the continuity of the following functions at x equals to 1. We are given 3 functions here. The first function is a linear function, which is 2x plus 3 if x is less than 1. Then for the second function, this is a constant function. We are told that 7, f of s equals 7 if s is equals to 1. Then we are told that s squared plus 4 if x is greater than 1. All right, okay. So we are also test the continuity of the function at s equals to 1. Most of the time, they will give you something like this. They will not even indicate at what point you are testing. We look at this function. From here, you can determine that we are testing for the continuity of the functions at s equals to 1. Are you there? Okay. So let's look at this first. The first is to define f of 1, right? F of 1. F of 1. If you look at these 3 functions, which of these functions will define f of 1? F of 1 means s is equals to 1. Which of these define f of 1? Definitely is the second function. We are told that x is equals to 1. So f of 1 is equals to 7. This is what defined, right? We have defined this. Number 2 is that we have to find the limit of this function. Since we have 2 inequalities here, we are told that x is less than 1 and x is greater than 1. Don't forget that we say that for a function, for a limit to exist, right, the limit of that function as s approaches a on the left hand side must be equal to the limit of that function as s approaches a on the right hand side. When you hear the word right hand side, it simply means greater than. Left hand side means what? Less than. So for limit of f of x as x approaches a to exist simply means that the limit of f of x as x approaches a on the left hand side, which is less than, right, must be equals to limit of f of x as s approaches a on the right hand side, which is what? Greater than. Don't forget, left hand side is less than, right hand side is what? Greater than. So let's find our limit. So here we can find the limit of f of x as s approaches a, okay, on the left hand side, because we are told that x is less than 1. Here we are told that x is greater than 1. Okay, this is not like the other examples we saw where we just find the limit of the function and we compare with f of a. In this case, we have 2 inequality. We have greater than and we have less than. So it means we have to find the limit on the right hand side and limit on the left hand side. So let's find the limit. Number 2 condition, limit of f of x, all right, as x approaches 1 on the left hand side. On the left hand side, we use the word minus on the left hand side. Which of these do we say we use to represent left hand side? Is 2x, meaning 2x plus 3. Now, to find limit of a polynomial, like a linear function like this, what do? We don't need to even rationalize. All we just need to do is direct substitution. So I will substitute the value of x as 1. So 2 times 1 plus 3, right? And that will give us what here? 5. So let's see limit of f of x as x approaches 1 on the right hand side. Right hand side simply means greater than, right? It means I'm going to use this to find the right hand side, which is s squared plus 4. S squared plus 4. So let's see what we're going to generate here. We have 1 squared plus 4. 1 squared is 1 plus 4. We have what here? 5. What you notice here, limit exists because the left-hand side limit equals the right-hand side limit. But f of 1 is not equals to the limit of f of x. So that means the function is not continuous at s equals to 1. Okay, so from here, lim f of x as s approaches 1 on the left hand side equals to lim f of x as s approaches 1 on the right hand side. Therefore, the limit of f of x as s approaches 1 exists, right? It exists and is equals to 5. Good. Okay, but f of 1 is not equals to the limits of f of x as s approaches 1. F of 1 is 7. 7 is not equals to 5. Sure, since the limit of f of x is not equals to f of 1, therefore, the functions is not continuous or are not continuous at x equals to what? 1. The function is not continuous at s equals to 1. We call this, is still a whole discontinuity function or a whole discontinuous function because f of a is not equals to limit of f of x. We also have a type called the jump discontinuity function or discontinuous function. Jump is experienced when the limit of f of x as s approaches a on the left hand side is not equals to limit of f of x as s approaches a on the right hand side. If here is 5 and here is 4, it means we experience a jump. I mean, limit does not exist. Whenever limit does not exist, like this, we have what we call a jump discontinuous function. Now let's see another example. We have seen this example. Let's see another example. All right, class, let's look at this example. We have to test the continuity of the functions. Here we are given 3 functions. Here we have the first function is with x plus 2. And we are told that if x is less than 2, second is x squared minus 2. And we are given a range of value. 2 is less than or equals to x, less than 3. Then with the third function is given as 2x plus 5, where x is greater than or equals to 3. If you look at this, we're not told to find the continuity of this function at a particular point. But looking at the range of value, the inequality sign given to us, we have 2 and we have 3. In this case here, we have that 2 is less than or equals to x, meaning the reverse says s is greater than or equals to 2. That means we have to test the continuity at s equals to 2. Also, here we are told that x is greater than or equals to 3. That means we also to test the continuity at x equals to what? 3. Are you there? So this is more like 2-in-1 question. So we're going to test the continuity of this function, f of x at x equals to 2, number 2 at x equals to 3. So the first one, for at x equals to 2, we're going to define f of 2, right? Let's define f of 2. Which of this function will define f of 2? Looking at this, here we have x is less than 2. This cannot define f of 2 because we don't have an equal sign here. But this can define f of 2 because we are told that 2 is greater than, is less than rather, or equals to x. The reverse of this simply means x is greater than or equals to 2. That means that if I'm to find the limit here is to the right, right? But the most important is how do we define f of 2? We have to choose this function. This cannot be used to define f of 2 because we are told that x is greater than or equals to 3. All right? This value here simply means number from 3, 4, 5, 6. This simply means number from 2, 3, 4, 5, right? So from here we have x is greater than or equals to 2. That same x is less than 3. So from here we can define f of 2. To define f of 2, it means I will choose this function. Alright? We have seen the reason why we cannot use this to define f of 2 because we don't have an equal sign. Suppose this equal sign is not here, but is somewhere here. It means to define f of 2, I have to use it to define it. But it's the reverse. Here we are given the equal sign here. So f of 2 is defined by using s squared minus 2. And that will give us what? 2 squared minus 2. 2 squared is 4. 4 minus 2, the answer is 2. Now, don't forget we are looking for the continuity at s equals to 2, the first one. So we have defined f of 2 and we got 2. Let's find the limit of f of x as x approaches 2. We can find the limit because we have x is less than 2. We have x is greater than or equals to 2 here. That means we can determine the limit of our f of x as s approaches 2 on the right hand side using this expression. On the left hand side using this expression. So let's find limit of f of x as s approaches 2 on the left hand side. We're going to use this to solve. That means root x plus 2. Why are we using this to solve? Because we are told that x is less than. Don't forget that less than means to the left, right? It means to the left. Greater than means to the right. This expression here means s is greater than or equals to 2. So that means to find my limit of f of x as s approaches 2 on the right hand side, which is greater than, I'm going to use s squared minus 2. But let's find on the left hand side. That will give us what here? Root 2 plus 2. And that will give us root 4. Root 4 and root 4 is equals to 2. So the next is to find the limit of f of x as x approaches 2 on the right hand side. Now, tell me which of these functions will I use to find my limit of f of x as s approaches 2 on the right hand side? Definitely is this, right? Because I said right hand side means greater than. This expression can be written as x is greater than or equals to 2. If 2 is less than or equals to x, that means x is greater than or equals to 2. So I'm going to use it to find my limit, which is s squared minus 2. All right. So there's nothing like factorization here. Suppose I have s squared minus 4. It simply means I have to factorize this. Right? Yes, of course, because by the time we put the value of x, I will have 0. But in this case here, we are told that s squared minus 2. S squared minus 2. So let's substitute that. That will give us what here? 2 squared minus 2. And that will give us 4 minus 2 equals to 2. What we notice that the limit exists. F of 2 is defined. F of 2 is defined because it's 2. Limit exists because limits of f of x as s approaches 2 on the left hand side is same as limit of f of x as s approaches 2 on the right hand side. Okay. Since lim f of x as s approaches 2 on the left hand side equals to lim f of x as s approaches 2 on the right hand side. Therefore, limit of f of x as s approaches 2 exists. The limit exists, but you should note that f of 2 is equals to the limit of f of x as s approaches 2. Our f of 2 is given as 2, and 2 is equals to 2. F of 2 will solve as 2, and limit of f of s as s approaches 2 is also equals to 2, because this whole thing is equals to 2. Limit on the left hand side is 2, right hand side is 2. So limit of f of s as s approaches 2 exists and is equals to what? To 2. So since our limit of f of x equals to f of 2, therefore the function is continuous. Therefore, okay, let me just say since, instead of saying but, since f of 2 equals to the limit of f of x, therefore the function is continuous at x equals to 2. Is continuous at x equals to 2. Now the second question says, is it also continuous at x equals to 3? Let's verify if it is continuous at s equals to 3. Let's verify if it is continuous at s equals to 3. Okay, let's verify at x equals to 3. So the first is to define f of 3. F of 3, which of these functions will be used to define f of 3? Which of these functions will be used to define f of 3? Definitely is the third function because we have an equal sign, right? So that means, yeah, we're going to have here to be 2x plus 5, and that will give us 2 times 2 times 3 rather, plus 5. Yeah, we're going to have here to be 6 plus 5 equals to 11. Now let's find the limit of f of x. Limit of f of 3 as x approaches 3 on the left-hand side. On the left-hand side. Here we are told that s is less than 3. So left-hand side, I will use this function, which is s squared minus 2, meaning 3 squared minus 2. Are we there? 3 squared minus 2. 3 squared is 9. 9 minus 2, we have 7. Our limit of f of x as s approaches 3 on the left-hand side is 7. We use this to find the limits of f of x on the left-hand side. So let's find the limit of f of x as s approaches 3 on the right-hand side. For right-hand side, we're going to use this to find it because we are told that x is greater than or equals to 3. Greater than simply means to the right, right? So we use 2x plus 5. And that will give us 2 times 3 plus 5, meaning 6 plus 5. This will give us 11. This will give us 11. So what do we notice here? We notice the jump discontinuity. The limit does not exist because the limit, okay, I will say since lim f of x as s approaches 3 on the left hand side is not equal because we have 7, right? Not equals to limit of f of x as x approaches 3 on the right hand side. 7 is not equals to 11. Therefore, limit of f of x as s approaches 3 does not exist. Does not exist. Okay. Since the limit does not exist, that implies that we have what we call a discontinuous function at s equals to what? 3. This function is not continuous at s equals to 3 because the limit does not exist. We call this type of discontinuous function a jump discontinuous function. A jump is experienced when the limit of f of x does not exist, meaning the left hand side limit is not equal to the right hand side limit. So the limit, the function is not continuous at s equals to 3 because the second condition failed, which is that the limit of f of x does not exist. Okay, let's see another example. All right, the next question said investigate the continuity of the function at s equals to minus 1. By now, we should be familiar with this. We're just solving more examples so that we can have complete and comprehensive knowledge, right, on this topic. So let's look at this. We are given that f of x equals to this, and we have to investigate the continuity of the function at x equals to -1. Okay, the first is to define f of 1, right? F of -1 rather. In this case, f of -1 is defined as what? As 5. This is defined because we are told that for the function f of s equals to 5, s is equals to -1. So that means to define f of -1, the answer is 5. We have three functions, 2s plus 5. Here s is less than -1. Here we have s squared plus 2. S is greater than -1. Here we have 5, where s is equal to -1. So to define f of -1, the result is 5. Now the next is to find the limit, right? Limit of f of x as s approaches -1 on the left-hand side. On the left-hand side, we have two functions that define both left and right. Here we are told that x is less than -1. Here s is greater than -1. So to define the limit of f of x as s approaches -1 on the left-hand side, I have to choose this because left-hand side means less than. So we choose 2x plus 5. And that will give us 2 times -1 plus 5. The result should be 3. 2 times -1 is -2 plus 5, which is equals to 3. Now the next is to find the limit of f of x as s approaches -1 on the right hand side. Let's see what we're going to have here. That will give us, on the right hand side, we're going to use x is greater than -1, which is s squared plus 2. That will give us -1 squared plus 2. The result is 1 plus 2 equals to 3. Now what do you notice? The limit exists. Limit actually exists. Okay? Limit exists. So limit of f of x as x approaches -1 on the left hand side is equals to limit of f of x as s approaches -1 on the right hand side. Alright? Which is equals to 3. Therefore, the limit of f of x as x approaches -1 exists, right? And the result is 3. It exists. Alright, because the left hand side limit equals to the right hand side limit. But f of -1 is not equals to our limit, since f of -1 is not equals to the limit of f of x as s approaches -1. The function is not continuous, right? The function is not continuous at x equals to -1. And we call this type of discontinuity a removable, or also called the whole discontinuous function. Removable is experienced when f of a is not equals to the limit of f of x. But we experience a jump when the limit does not exist. Now let's see another example. Okay, let's see more examples on this. We have that f of x is given as this, and we have to investigate the continuity of the function at x equals to 1. All right, and f of x is given as, we have two functions. The first function here says x squared minus 4x plus 3 divided by x squared minus 1, but x must not be equals to 1 before, because if s is equals to 1, by the time we put the value of x as 1, that will give us an indeterminate or an undefined function. Number two function says 2, but x is equals to 1. But we are asked to investigate the continuity of the function at s equals to 1. So the first is we have to define f of 1. F of 1 is already defined as 2. It's defined as 2. It's defined as 2. Now the next is to find the limit. In this case, we are just giving two functions. We don't have an inequality sign here. No need to find the limit on the left hand side and right hand side. All we just need to do is to evaluate this to find the limit of this function. Then we'll compare our f of 1 with the limit of this function. But let's find the limit of our f of x, right? As x approaches 1. Okay, here we are given our x squared minus 4x plus 3 divided by x squared minus 1. If you look at this very well, if I'm to use direct substitution to find a limit, I'll definitely have an indeterminate form, right? That's why we are told that x must not be equals to 1. Meaning by direct substitution, this will give us, let's try it and see, 1 squared minus 4 times 1 plus 3 divided by 1 squared minus 1. This will give us 1 squared is 1 abi. 1 minus 4 will give us minus 3. Then we have plus 3 divided by 1 minus 1. This will give us 0 over 0. I will send it now. So that means that we cannot use direct substitution to find the limit. We have to factorize. We say we have the first method, which is direct substitution, right? Substitution. Number 2, we have by factorization method, right? Factorization method. Number 3, we have by rationalization method, right? And we say that the only time we use this number 3 method is when we have a square root. So there's nothing like square root here, so I cannot even use this to solve. So I have to do what somebody factorize this expression to find the limit of my f of x. Please ensure you watch my video on limit of a function. I did a comprehensive full tutorial on limits. It will really help you a lot. So let's factorize. Okay, so factorizing to find the limits of the function So let's go. So we have lim f of x as s approaches 1. This will give us. Now let's factorize it. This is a quadratic equation, so we can factorize, right? This one we can also factorize this using what we call difference of 2 squared. Am I communicating? So look at this now. The first term here is s squared. The last term is what? Is 3. Multiply the first term by the last term, we have 3s squared, right? Think of two numbers. Think of two numbers that once you add them together, the result will give us minus 4x. Minus 4x. This minus 4x here. The product of this and this gave us this. Now, let's find the two factors that once we multiply them together, we're going to have 3s squared. But when you add or subtract, the result must be minus 4x. Let's think. Definitely, the two numbers will be minus 3x and minus 1x. Let's verify. Minus 3x times minus 1x is 3s squared. Minus 3x plus minus 1x give us minus 4x. So when you add up this together, we have minus 4s, which is this center term. When you multiply them together, we have 3s squared. That means that these two numbers, right, we have to replace minus 4. And that will give us what? We have s squared. So we have minus 3x minus 1x is same as minus x. So here will be minus x plus 3, all divided by, I can express this as s squared minus 1 squared, right? Okay, because we are factorizing. So let's finish up this. All right, so the result becomes lim f of x as s approaches 1. Here we're going to have, let's factorize, s is common. Here we have x minus 3, right? Between this, what is common is minus 1 is common. In bracket, we have x minus 3. All right, okay. All divided by, By using the principle of difference of 2 squared, if I have a squared minus b squared, the result says what? A plus b times a minus b. We call it difference of 2 squared, right? Difference of 2 squared. So this will give us x plus 1 all squared and x minus 1. Sorry, x plus 1 times x minus 1. So our limit of f of x as x approaches 1 will then be x minus 1 times the two factors here becomes x minus 1 and x minus 3 divided by x plus 1 and x minus 1. Definitely, x minus 1 we cancel out with x minus 1. We are left with x minus 3 divided by x plus 1. So let's put our value of x. So the limit of f of x as x approaches 1 will then be 1 minus 3 divided by 1 plus 1. 1 minus 3 will give us minus 2 divided by 2. So when you divide minus 2 by 2, we're going to have here as minus 1, right? Minus 1. So our limit of f of x is simply equals to minus 1. Limit is minus 1. When you divide this with this, we have minus 1. But let's verify. Our f of 1 is defined as 2. Our limit is minus 1. Are they the same? No. Since f of 1 is not equals to the limit of f of x as s approaches 1, therefore the function is not continuous at x equals to 1. Okay, so let's finalize. Since f of 1 is not equals to the limits of f of x as x approaches 1, the value we have here is 2. 2 is not equals to what we have here is minus 1. Therefore, the function is not continuous at x equals to 1. We call this a removable or a whole discontinuous function because f of a is not equal to the limit of f of x. It's called a whole or a discontinuous function. Let's see another example. All right, guys, let's look at this example. We are asked to investigate the continuity of f of x at s equals to 2. We are given two functions. The first function is s squared plus 1 if s is greater than or equals to 2. Number 2, the second function is 7 minus x if x is less than 2. So the first step is to verify if f of 2 is defined. Since we are given two functions, we have to ask ourselves which of these can we use to define f of 2, because we are to determine if the function is continuous at s equals to 2. So we have to look at the two functions and we have to look at their conditions, right, given to us. Here we are told that x is greater than or equals to. Since I have an equal sign here, it means I will use this function to define f of 2. Here there's no equal sign, so I can't use it to define f of 2. Suppose this sign is here. It simply means I will use this function to define f of 2. But it's the reverse of this. So we are told that x is greater than or equals to 2. To define f of 2, we have to use s squared plus 1. And that will give us 2 squared plus 1. 2 squared is 4 plus 1 is 5. So the next is to find the limit of f of x as x approaches 2. On the left hand side simply means less than. Which of this function is x is less than? To find the limit of my f of x as s approaches 2 on the left hand side, we have to use this, right? Because we are told that x is less than 2. So that means 7 minus x, and that will give us 7 minus 2, which is equals to 5. The next is to find the limit of f of x as x approaches 2. On the right hand side, we are to use this function, but we are told that x is greater than 2. Alright, so that means we have to use x squared plus 1. And that will give us what? 2 squared plus 1. This will also give us 2 squares. 4 plus 1 is 5. What do you notice? That f of a is defined. This is defined, Abby. Is defined. It is not an undefined function because we have a real value, which is 5. Limit of f of x exists. So since f limits of f of x as x approaches 2 on the left hand side equals to limits of f of x as x approaches 2 on the right hand side, they are both equal. Therefore, limit of f of x as x approaches 2 exists and is equals to, we know the value, which is 5, right? Also, since f of 2 is equals to limits of f of x as x approaches 2. Since f of 2 is 5 and the limits of f of x from left hand side and right hand side, they are both equals to 5. So since f of 2, which is 5, is equal to the limit of f of x, meaning 5 is equals to 5. Therefore, we can conclude that, therefore, the function f of x is continuous at s equals to 2. Is continuous at s equals to 2. Now, last example, then we end this class. The last example, then we end this class. Alright guys, this question said find the value of k that makes f of s continuous everywhere. Now we are given the first function as ks squared if s is less than or equals to 2. The second function is given as 2s plus k if s is greater than 2. Alright, for this function to be continuous everywhere, the limit of f of x as s approaches 2 on the left hand side must be equals to the limit of f of x as s approaches 2 on the right hand side. By the time we equate both limits from the left hand side and the right hand side, we can be able to determine the value of k. So let's see. Solution to this is that the limit of f of x as x approaches 2 on the left hand side. Which of these are we going to use to find the left hand side limit? Definitely is ks squared because we are told that s is less than or equals to 2. So that means ks squared, and that will give us k times our x here is 2 or squared equals to 4. What we do here is that to find the limit of f of x, we have to substitute the value of x as 2, and that gives us k times 2 squared, which is equals to 4k. So this is the limit of f of x as s approaches 2 on the left hand side. Let's find the limit of f of x as s approaches 2 on the right hand side, which is this, right? That will give us 2s plus k. That will give us 2 times 2 plus k. 2 times 2 is 4 plus k will give us 4 plus k. Therefore, for f of x to be continuous everywhere, we say that limit of f of x as s approaches 2 on the left hand side must be equal to limit of f of x as x approaches 2 on the right hand side. Okay, on the left hand side we have 4k must be equals to, on the right hand side we have 4 plus k. So what we do here is to collect like terms, right? Collect like terms, and that will give us 4k minus k. When we move this to this side, or we subtract k from both sides, right? Or move this to this side, that will give us 4k minus k equals to 4. All right, so 4k minus k give us 3k equals to 4. To find the value of k, we have to divide both sides by 3. Okay, that means this will give us k equals to 4 over 3. This is the value of k that makes f of x continuous everywhere. That is the value of k, which is 4 over 3. Alright guys, so we're going to stop here for today. Then in my next class, we'll be talking about calculus in detail, which is under differentiation and integration. So it is a class you cannot afford to miss. Ensure that you subscribe to this channel. Ensure you share this video to your classmates. There are many people who are looking for this opportunity to learn. All right, these are examples from your past questions. Okay, that is for those of you who attends Imo State University. These are examples, and these are the things you'll be seeing in your exam. All right, please make sure you share, like, comment, and also subscribe. Thank you so much. I'm grateful. So see you guys in my next class.